Welcome to a new episode in the Multiverse video series. I'm Javier Luraski, and today we're going to talk about how to do geospatial analysis using Apache Spark. So, what exactly is geospatial analysis? Well, a very high-level introduction to this, we can present it using Google Maps. And we are all familiar with Google Maps. Basically, it's a great tool to let us search for local places and get directions from different cities and why not. And when you think of Google Maps, basically, you can think of kind of like geospatial processing. Whenever you have a data set that involves a longitude and a latitude, that means whenever you have a data set that has points in space, you should consider using geospatial analysis. This is especially important when you're dealing with big data. Why? Well, you will have to kind of like take special considerations when dealing with geospatial data because the computation can be quite tricky if you don't use the right tools. So let me introduce you specifically to spatial analysis. So in the same way that you can do, like tabular data analysis for data sets that, like follow a tabular data format and why not, there's a specific constraints and considerations that you need to take into advance whenever you're dealing with spatial data sets. So for instance, in this case, from the Wikipedia page, we can see that there's a very small data set showing basically data from London. This is probably quite old, and why not? But as you can see here, there's different points of interest that are laid down in this particular map. And this is what we could consider a spatial data set. And, if you don't have that much data, you can probably use R and tools available in R to process these kind of data sets. But when you have data sets that contain millions or billions of points that you need to process efficiently, then you can start considering combining both Spark with GeoSpatial processing. So how exactly do you do spatial processing? Well, we're not going to get into a lot of the details, but the tricky thing is that you can't really use the same algorithms that are available in bare bones Spark or in bare bones R. Well, why? The reason is that usually most data analysis tools like R and Python and Spark, they're optimized for numerical data and for relational data. And datasets are kind of like a different type of dataset. As I was mentioning, there's datasets that include a longitude and a latitude, which in this case, could look like something like this. And without getting into too many details, there's basically a set of algorithms that are much more efficient in dealing with data that has X and Y coordinates. One of these particular data structures is called a quadtree. And basically what a quadtree does is rather than indexing, each column, from longitudes and latitudes, what it does, it divides the space in 4 different regions. So as you can see here, kind of like there's 4 major regions, the top left, the top right, the bottom right, and the bottom left. And a way of indexing points that makes searching and other operations that we'll talk about, that makes this much more efficient is by basically dividing in spatial with a spatial index, which in this case is by dividing in areas of like 4. And then what happens is like you can subdivide that particular area in 4 again and 4 again, and why not? Now, you don't need to get into the details of these, but what is important to notice is that when doing geospatial analysis, you want to use the type of tools that support these operations, because otherwise computation is just going to be too expensive. So this is another representation of a quadtree. If you're familiar with indexing and binary trees and things like that, Usually databases index data in trees. What the type of tools that we need to do efficient spatial analysis at scale are tools that support indexing data geospatially. And again, we don't need to talk about the details, but knowing that there's tools optimized for searching, retrieving, and joining datasets that are spatially located, it's important for this video. So one of the packages that the Spark community has developed that allows you to load large datasets into Spark and process large data in Spark that is spatially annotated is the GeoSpark extension. This is an Spark extension that makes use of core technologies in Spark like RDDs and SQL and things like that, and basically allows you to make use of this type of spatial indexing at scale on Spark. So I decided to record this video today because there is a new extension today in CRAN called GeoSpark that expands Spark, and it's available in R. This extension is an extension that uses the dplyr package, and it was developed by Harry Zhu. And the great thing is that you can basically do spatial analysis in R using Spark very easily without without having to get into all the complexities of like quadtrees and how exactly things are getting stored in a distributed large dataset. All right, so how exactly does this look in Spark? So first of all, you want to run install packages GeoSpark, which I already run for you. And after you run GeoSpark, after you install GeoSpark, you wanna load GeoSpark, which is the library that we're gonna use to do geospatial processing in Spark with R. And then you want to load dplyr as usual. Then we want to connect. In this case, we're going to use a local cluster, but if you were to have an actual Spark cluster, you can basically make use of your cluster manager and specify it right there. Right. So we're connecting, and as part of this connection process, we're also loading the GeoSpark extension and the GeoSpark library, which is quite helpful in this case. Okay, this is great. So the first thing to note is that geospatial datasets look quite different from the ones that you're familiar with. This package already comes with a sample dataset. It's under examples. And then it's called polygons.txt. Let's make sure that this works. All right, and if we were to read the lines just for fun, to get a sense of how this looks like, you can see that this dataset contains a set of geospatial coordinates. So for instance, it defines an area called California with a polygon, and this is an arbitrary polygon that sets position on the XY coordinates, or more specifically, longitude and latitude. And basically, it probably approximates, in this case, a region that might be California. Now, this is a pretty simplistic polygon. Like if we were to actually define how California, the California state looks like, it would be quite a large region. And combine if you combine that large region with a lot of points, you can see how this can start getting quite complicated pretty fast. So for instance, one of the other datasets that are included in this package is the points dataset. And again, it's pretty small. It's just an example. But what this particular dataset describes is a set of cities, right? So you can say, for instance, New York is defined on this particular longitude-latitude coordinate, and Floral Park, or like Austin in somewhere else, and why not? And then you might want to ask yourself, okay, which of these cities are inside the states that we're defining above, right? And like this can be done quite easily if we were only working with small data sets. If you have huge data sets, you want to make use of the computation power of Spark and smart algorithms like quadtrees and why not that allows you to actually compute these operations efficiently. All right, so the first thing that we want to do is let's just load in memory these two data sets because they're basically defined on a line-by-line cases, and it comes with a few separators that you might have already noticed using the pipe operator. So let's see if this works. And the only thing that we're doing here is basically just loading the files in memory. In most cases, what we would actually do is load these directly into Spark, but just to get an idea of how this is looking like, we're going to use this particular method. All right, so we're using read table, and then we're basically need to also specify the column names. Yeah, so let's specify the first column, in this case called area, and the second one is the geometry, which is actually the interesting data part of the data set. Like, I mean, we know how to load columns in Spark. That is not that, let's call that's not that hard to load columns, and why not? So we're really going to focus on the actual geometry column in a second. Okay, so now let's load the points directly again, just in R because they're small enough. We'll call these points. And in this case, the columns are going to be different. As you can see, we have, we actually loaded the previous one incorrectly. Let me just fix the column area. All right, let's try that again. Okay, now let's load the points from the same package, and the columns are different. In this case, the first column is the city, followed by the state, and finally the geometry. All right, so we have the points, or we should have the polygons, and we should have the points loaded. Now we actually want to load this into Spark, and again, if this was a large data set, what we would actually have done would have been to use Spark read text, and we would have loaded that directly into Spark. But instead, what we're going to do is we're just going to use the copy to command to copy into Spark polygons, and we're also going to copy into Spark the points. Let's just rename these. We have the points. If you're trying to figure out why I'm calling these WKT, as I mentioned, the most interesting part here is the geometry, and the geometry comes in a format called well-known text. And we can abbreviate that by calling it WKT, and that's going to be the interesting piece that we want to use in Spark. All right, so now let's load dplyr. But again, dplyr in this case is not going to be very good at dealing with these particular data points because they're regions, and so we need to make use of in this case we need to make use of the GeoSpark extension to actually do interesting things with this. All right, so let's actually rename a couple things. We're going to rename the polygons. We're going to transform it a little bit. So we can use mutate for this particular data set, which we already have loaded into Spark. And we're just going to, we just need to actually load the data into geospatial data. As I mentioned, currently what we have is what is known as a well-known text format. What we want to use is a helper function from GeoSpark that GeoSpark defined called st underscore geometry from well-known text. And this is the geometry. So basically, all that we're doing is asking GeoSpark to load the well-known text as an actual geometry, which means that it will also get optimized for subsequent reads and writes, and why not. let's see if we got this right. Seems we did. Let's just double check. Yeah, so as you can see here, sparklyr is retrieving this as a list, but the data type is a polygon, and it's actually the correct data structure that we want to have in GeoSpark. So let's do the same with points. We're gonna create now another variable. Let's just call it x. And actually, the name of the column is the same, is geom, but we don't want to use polygons. We want to use points. All right, so let's try that again. And we should have another column, which is x, that contains basically the actual geospatial data. Now, there's lots of ways in which you can join different tables in dplyr, and we can still make use of these, but there's a trick that we need to do in order to make it this efficiently. So let's join both tables. We'll join the polygons table, and let's join it with the points table. But dplyr doesn't know anything about geospatial data on its own, so either you will have to do the mathematical computations yourself, which is really, really hard and inefficient, or you can prepare the join for dplyr, and when you're doing the join, you can actually ask dplyr to use a custom join statement, which you can specify with the SQL on parameter when using inner joins. And then what we want to do is we're going to use a bare bones SQL statement, and specifically we're going to use here st contains y comma x. All right, so what we're doing here is we're finding points that are contained in the region that we're defining from the points dataset. And once we do that, let's see if this runs, which it should. And after this, we can basically use any of our well-known dplyr comments to kind of like process this a little bit nicer. So we can group by, let's say, by area and state. And then we can summarize. And, you know, since we're actually joining these two tables, what just check this count. Should be familiar. Okay, we're getting an error. Let's see. No need to panic. Area given input oh, okay. So as you notice, I actually misspelled the area column. I don't know why I didn't rerun this. So one of the previous statements that we have here, I believe was the original one actually. So even before we copy it, yeah, see, so this particular statement, it's already incorrect. So we have two options. Either we can go and fix the column, which we can do, is not a big deal, or we could just misspell the column in our SQL on our dplyr statement. So let's just do the right thing, which is fix it. So here, when we were loading the actual polygons, yeah, so yeah, when we were loading we load the points, and somewhere in here we also load the polygons. Was it this one? Yeah, so this one is misspelled. Okay, so let's try everything again up to this point. So we have the area, and we also need to copy this file again, correct? So we're gonna copy polygons with polygons. Let me just really quickly overwrite it. All right, and we also perform a mutate statement to actually load the geometry, which we need to rerun. All right, so let's try this again. We were running basically our inner join, and we were grouping by. All right, and this works because we actually have the variables correctly spelled. So now we could actually count for each particular area how many cities are in there. You can see that California has 10 cities, New York 9, the Dakota area has 10, Texas 10, and Dakota area from a different state only has 1. And we could verify this, and why not? But yeah, this is actually pretty great because it was quite easy to do a geospatial query asking within a polygon which are the cities that are contained. But again, like when you have a lot of points and when you have more complex polygons, these can actually be a pretty quite expensive computation that would require significant compute instances just to get this going. So before we finish this video, I want to give you an overview of what are the other operations that you can do. So as mentioned, what we just used in this video was stcontains, right? So stcontains looks more or less like this. You give it a in this case, which was our points or our cities, and you give it a region, which is B, and it will basically join based on the cities or the points that are contained within that region. However, there's other operators that you can do, and while you're performing a join with dplyr and GeoSpark, for instance, you can find out which are the regions that are disjoint, or the regions that touch, where there's overlap, like not an overlap, but where they touch to in their boundaries between them. You can use st crosses if there's an actual cross between the regions, or equal if the regions are actually equal. Then you have st within, which is similar, and st covers, which there's a couple few peculiarities here, but what is worth mentioning is that each of them have like slightly different purposes, and it's something that you want to kind of like look and describe on their particular documentation of the GeoSpark project. You can probably pretty easily find like the specific definitions of each of them, and yeah, it shouldn't be that hard to actually get a good description of each of them just by searching in their actual documentation. All right, well, I'm hoping that this video was useful. Definitely spatial data is quite common and can be quite hard to process at times when the data sets are large and when the regions are quite complex. So for those cases where when you are actually dealing with spatial data sets, you can consider using Apache Spark with R and the new GeoSpark extension to get things up and running quite easily. Right, well, thank you so much.